Swayam Prabha. Digital India. Educated India.
Till now we have studied very simple rotor models with mainly we considered the transverse vibration of the rotor system. Even we incorporated some complexity in some cases in the bearing in the form of various spring and dampers, and even we considered complexity of the gyroscopic couple onto the rotor. But till now we have not considered the other type of vibrations, especially the torsional vibration, which occurs in various turbo machineries. So today we will see very basic concepts of the torsional vibration, and then we will analyze some simple rotor like single mass rotor and two mass rotor today, and then subsequently we will be analyzing more complex rotors by more systematic methods like transfer matrix method, finite element method. So today we will be introducing very basic concepts of the torsional vibration. So this is the overview of the lecture, in which I will be introducing torsional vibration of single and two disc rotor system, or even if these discs are connected by stepped shaft, then how the torsional vibrations will be analyzed, we will try to see. We will do some kind of equivalent shaft system, and then we will analyze this particular system. The basic concept which we will be covering is torsional vibration, torsional natural frequencies and mode shapes. Even we will be having concept of the node positions and equivalent system, especially for the stepped shaft. So this is a typical application where we can have torsional oscillation. There is a geared system in which we transmit lot of power, and these gears gives impulses in the form of torque, and this may give torsional excitation in the form of external excitation. And if any of the natural frequency in the torsional mode is coinciding with the gear mesh frequencies, then we may have torsional oscillation in the resonance conditions in the system. Similar to the gear system, we have some other systems in which we can have torsional oscillation, like if we have some applications where we like punching of blanks in a sheet, in that we have in that particular case we have the sudden change in the energy of the flywheel in a very small duration during the punching, and remaining time it stores the energy. And in these generally we use flywheel, and that is mounted on relatively flexible shaft, and because of this variation in the energy in the form of torque, we can have torsional critical speed or torsional resonance condition in such systems. Even in systems in which we have rotating machineries, especially rotating or especially the reciprocating engines, we can have this kind of torsional oscillation in which variation of the torque take place because energy or the torque variation is periodic in nature, and because of that we can have torsional resonance condition in reciprocating engine system. Apart from that, if there is a fluctuation in the torque in any form in rotating machinery, either that is due to the fault in the electric system or maybe due to the rubbing of the rotor with the stator, we can have torsional oscillation in the system. And if these excitation frequency, external excitation frequencies in the form of torque coincide with the torsional natural frequency of the system, we can have resonance condition. So now let us see what is the torsional oscillation with a simple model. So in this particular case, there is a thin shaft and a relatively rigid disc, and the torsional oscillation is nothing but if we give a twist to this and leave it to oscillate. So you can able to see that if I am giving a small twist, this disc oscillate about its mean position, about its own axis. So the frequency at which it is oscillating, because this particular shaft is relatively rigid, so and a lot of damping is there, so the oscillations are 1 or 2, but if the damping is less, which is in most practical case, we can have large oscillations, and we can have continuous oscillation of this. And as we know, these machineries rotate at high speed, and apart from this, the nominal speed of the rotation of the shaft, it can have oscillation about its nominal speed. So is something like the spin speed of the shaft, and these torsional oscillations are superimposed on each other. So we can see the net effect of that. The speed variations will be there about its nominal speed because of the torsional oscillations. So with this simple model, we have seen how a relatively heavy disc, which is having large polar moment of inertia, and the shaft having torsional flexibility, can produce torsional oscillations about its own axis. And this particular when we are disturbing the system with some kind of initial disturbance, and whatever the frequency of oscillations take place without any external excitation, that is the torsional natural frequency. And if any of the external torque which is coming onto the system coincide with this natural frequency, then we will be having resonance. So let us take very simple rotor model in which we have a relatively thin disc. It is having torsional stiffness, let us say KT. This is the relatively thin shaft, and this is a flexible mass or polar mass moment of inertia of the shaft we are neglecting. This is a thin disc which is at the free end of this particular rotor system, and we have oscillation of this, let us say phi z about z axis, this axis is z. So this is the rotational displacement of the disc about its own axis. In this particular case, you can see this is a very simple rotor model in which we can able to obtain the system equations by first drawing the free body diagram of the disc. So if we remove the disc from the shaft, let us say we have the torsional displacement counterclockwise direction, positive sign, and if we are giving a displacement in this direction, the resistance from the torque or from the shaft will be opposite. Let us say this clock, clockwise it will be acting. Let us say that is Tz, and this is the only reaction torque which will be acting on to the disc. So, we can able to write the equation of motion of this by Newton's law by summing up all the external torque on this. So, external torque is only Tz, which is acting negative direction to the displacement, because this is a reactive torque from the shaft onto the disc, and this should be equal to the inertia of the disc. So, this is the rotary inertia of the disc. We are equating it to this much. Now, this particular torque is coming from the this stiffness, torsional stiffness. So, we can replace this torque with the expression of the kT into the displacement, angular displacement which we have given. So, this will be equal to IP. So, now we can able to write this in more standard form, which is a very familiar equation similar to mx double dot plus kx is equal to 0. Only thing is, in place of mass, now we have polar moment of inertia of the disc, and the stiffness is torsional stiffness. This torsional stiffness we can able to obtain from the theory of torsion. So, we know from strength of material this relation, in which T is the torque, J is second moment of area, that is polar second moment of area. If for circular shaft with diameter d, G is given by this expression. G is the modulus of rigidity, theta, or we can able to replace this theta by, let us say, phi z, angular displacement, and L is the length of the shaft. So, length of the shaft is L. So, this torsional stiffness is nothing but torque divided by the angular displacement, similar to the force divided by linear displacement. So, because here motion is in angular displacement, so we have torque divided by this is the torsional stiffness. From this expression we can able to see, we can able to write this as G J by L. So, this particular torsional stiffness is given by this, and which is depend upon the length of the shaft or diameter of the shaft or dimensions of the shaft and the material property. And from this is very clear from the previous understanding of the single degree of freedom system, we can able to say the natural frequency will be given by the stiffness divided by the polar moment of inertia, that is k by m. So, this is the natural frequency of a simple single degree of freedom rotor system for torsional oscillation. So, this is torsional natural frequency. This frequency will be obviously different as compared to the transverse natural frequency which we obtained earlier. In that particular case, we wrote this particular natural frequency for transverse vibration as k by m, where m is the mass of the shaft, k is the stiffness of the shaft in transverse direction. So, that expression will be different as compared to this one. And from here it is very clear that the torsional natural frequency and the transverse natural frequency will be different, and they will not be same for the same system. So, from the simple analysis of rotor system for torsional oscillation, that is for single degree of freedom, is clear that we have torsional natural frequency similar to the transverse natural frequency which we had earlier studied. Now, we will take some more complex rotor system. Let us now take two disc system, two discs, and that is connected by a flexible massless shaft, these discs are having polar moment of inertia IP1 and IP2. The shaft is having torsional stiffness KT. The shaft is having torsional stiffness KT, and this shaft is supported, let us say, on frictionless bearing, so that these discs can have angular displacement. I am taking both as counterclockwise direction as positive. So, these bearings are not providing any friction, and these, so basically when this particular system is under torsional oscillation, when this system will be under torsional oscillation, the boundary conditions will be something like free boundary condition, because there is no as such support which is restricting the motion of these two discs. So, boundary conditions, free boundary conditions, and to obtain the equation of motion of this, obviously our aim is first to obtain the natural frequency of the system. For that we need to obtain the equation of motion of the system. So, for this we will draw the free body diagram of both the disc, and from there we can able to obtain the equation of motion. So, let us see the first disc IP1. In this we have taken counterclockwise direction for the angular displacement as positive, and because of this the torque will be opposite, that will be clockwise. So, this torque is KT, and the relative twist, because the torque which will be exerted from the shaft on this disc will be relative displacement between these two discs. So, basically this shaft will be getting twisted by the relative displacement of these two. So, that is this one, 1 minus 2. So, this is the free body diagram of the disc 1. Similarly, we can able to draw the free body diagram of disc 2. In this we are taking the angular displacement as obviously counterclockwise direction, because this particular torque, which is reaction torque from the shaft, this particular torque will be acting here, that will be same, because this is the torque which is transmitting from the shaft, but it will be acting opposite to that. That means, if we have a free body diagram of the shaft, so obviously this torque will produce a reaction here. So, this is in the clockwise direction. So, here we will be having torque, same torque, but opposite to that, and here again we will be having opposite to this one, and the torque here will be opposite to this. That means, it will be, this is clockwise, so that will be counterclockwise, and the value will be same, this one. This is clockwise, and this should be counterclockwise, and value will be the same. Now, we have free body diagram of the disc 1 and 2, and from this we can able to obtain the equation of motion by equating the external torque to the inertia. So, for first disc we can able to write KT. This is the external torque which is acting onto the disc, should be equal to the inertia of the first disc, this one. And in this particular case, second disc we will be having, this is negative because this is clockwise, this is anti-clockwise. Here both are same direction, counterclockwise. So, we will be having KT phi z1 minus phi z2 is equal to IP2 phi double dot z2. So these are the two equation of motion which we can able to write in more standard form. In the next slide we can write. So these equations are, if we write again here, this is the first equation. Second equation is kt only, kt1 is not there, phi z2 minus this is kt only, same, only single shaft is there. So these are the two equation of motion of the this particular system, in which we have two discs connected by a flexible shaft, and there is no as such support which is giving a torque, external torque to the system. So these two equations we can able to now write in matrix form that will be convenient to handle. So I am writing them in a matrix form. So here we will be having IP1 0 0, IP2 plus this is stiffness terms. There is no external force, so right hand side is 0. Here we will be having KT minus KT. So this you can able to see, this is the, if we expand this matrices we can get back these two equations, and okay, so we can able to write this is in more standard form, like a matrix M, mass matrix, and angular displacement, there is acceleration, plus stiffness matrix and angular displacement vector is equal to 0. Now we can able to choose the angular displacement, which is function of time, as a amplitude part of the displacement, and the harmonic part. Omega nf is the natural frequency of the system, torsional natural frequency of the system, and this is the amplitude and phase informations will be here. The form of this amplitude will be for both the discs like this. Now we can able to take derivative of this once more, double derivative. So we will get minus omega nf square phi ej omega nft. Now this assumes solutions, and its derivative we can able to put in the equation of motion. So we will get a matrix, then we have capital phi or e j omega t, time dependent term I am taking out as a common. So because we can able to, because this cannot be 0, so we need to eliminate this. Here also we can able to see, we can able to simplify this as k minus omega square nf m, then phi vector we can able to take common, is equal to 0. So this is a typical homogeneous equation or eigenvalue problem. One of the solution of this is that this particular displacements are 0. That means both the discs are having 0 displacement. So we are not interested in that, in which basically we are talking about the system when system is not vibrating. So, to have a non-trivial solution of this, obviously we need to take the determinant of this to be 0, and that will, this particular matrix now I am writing as a determinant. So, we had KT minus IP1 omega NF. So, this is first term of these two, minus KT and then KT IP2 omega NF. So, this particular determinant is the summation of these two. So, when we take a determinant of this, we will get a polynomial in terms of omega NF square, that is the natural frequency of the system which we want to obtain. So, we will get, after simplifying the determinant, this term IP1 plus IP2 omega NF square KT is equal to 0. So, here we can able to see that omega NF square is common. So, if we can take out that also, so we will be having 1 IP1 IP2 omega NF square IP1 plus IP2 KT is equal to 0. So, from here this last equation is clear that one of the natural frequency is becoming 0, and the terms within the bracket also we need to equate it to 0 independently. So, from there we will get another natural frequency. So, we are getting two natural frequency, one is 0 natural frequency, and from second term within the bracket if we equate, we will get this expression for the second natural frequency of the system. So, in this particular case you can see this is 0 natural frequency. This particular natural frequency we will see what is the physical interpretation of this. For that we need to obtain the mode shape of the system. In the mode shape actually is nothing but how the two disks are oscillating with respect to each other relative to each other. So, in this particular case we will see that when the natural frequency is 0, both the disks will be having identical displacements. So, that means both the disks will not be having any relative twist between them, and because of that the shaft will not get twisted. So, we will refer this particular oscillation as rigid body mode, and how to get this, let us see how we can able to get this particular mode shape. So, if we go back to the equation, this equation, so as we know these are two equations. So, I am writing this in the expanded form again for the clarity. So, we have KT minus KT, this is stiffness matrix minus natural frequency IP1, IP2, and outside we have displacement amplitude, complex displacement amplitudes, this. So, now if we take first equation, let us say, that is KT minus omega NF IP1 into this displacement, first term, then minus KT phi Z2. So, I have taken the first equation of this whole matrices. So, if we put one of the natural frequency which we obtained, let us say first natural frequency in this particular expression, we will see that this term will vanish and we will left with kt phi z1 minus kt phi z2 is equal to 0, and this gives us that when the system is oscillating at 0 frequency, their displacement must be equal, and we can able to now make out when both the discs are having same displacement, the shaft will not be having any twist, and so we call this as rigid body mode. And as such, this, because there is no stresses in the shaft, is not of practical importance. Now, the second natural frequency, if we substitute in the same equation, we can able to get for this natural frequency what will be the relative displacement between the two discs. So, now in the next slide I will substitute this one in the same equation. So, we have kt minus omega square is kt ip1 plus ip2 divided by ip1 ip2. So, this is this expression plus into ip1 and whole is multiplied by phi z1, and the previous expression is this one minus kt phi z2 is equal to 0. And if we simplify this expression, we will get z2 by z phi z2 by phi z1 as minus of ip1 by ip2. So, here you can able to see that the relative displacement between these two discs will be inversely proportional to the their mass moment of inertia, polar mass moment of inertia. So, we expect that in this particular case, when if one disc is lighter and another is heavier, the disc which is heavier will be having less displacement as compared to the disc which is lighter. And in this particular case, the negative sign is there. So, even the motion of these two discs will be opposite. So, if we have two discs, if one is rotating in clockwise, another will be rotating in anti-clockwise direction, and if the motion reverses because of the free vibration, then both the discs will be having always opposite motion. So, if we want to draw this particular motion, so you can able to see that in the first case when the natural frequency was 0, if we want to plot the relative displacement between two, so this is phi z1 and this is phi z2, because both are same. So, the shaft will be having as such no relative twist, is a rigid body mode. And for second natural frequency, as we have seen in this particular expression, if we have displacement of one disc in the positive direction, the other disc should have the negative displacement, and the shaft displacement will be varying linearly in between. So, you can able to see that the shaft is having maximum displacement here and here, and their amplitude will be inversely proportional to their mass polar moment of inertia, and in between you can see that there is a one position where the displacement, angular displacement is 0. So, this particular position is called node, and you can able to see that there is no angular displacement here, and either side of this the angular displacements are opposite to each other, because this is positive and this is negative. So, as such this particular node we can able to think of as a rigid support. So, what we can able to idealize this 2 mass rotor as 2 single degree of freedom rotor system. Let us see that particular equivalent concept. The 2 disc rotor system which is there with us. In this particular case, when we are drawing the mode shape, depending upon the stiffness and the polar moment of inertia of the disc, we will be having node at some intermediate position, not necessary at the midpoint of the shaft. So, this node position, what I am saying, because here displacement is 0. So, corresponding to the left hand side, the system which is there, the shaft and the disc, and in the right side which is there, because at the node position there is no displacement. So, 2 rotor system which is having 2 degree of freedom system can be idealized by 2 system having single degree of freedom system, and in this particular case they are cantilever rotor system, and this is both the systems should have the same natural frequency, because when we are considering the motion of this, obviously for second mode both the discs are having same angular displacements, the same angular frequencies. So, these 2 systems which are equivalent to this, dynamically they will be same only when the natural frequency of this system and this system are equal. So, that means if we have the length of the shaft is, let us say L here. So, let us say the node position from the left disc is L1 and here it is L2. So, this will help us in finding out the node position. So, for first case we can able to write the natural frequency of the system as stiffness KT1, let us say IP1, where KT1 is GJ by L1. For second system, this system we have, so this is corresponding to this one, and for second system we have the same natural frequency because it cannot be different, and they are corresponding to the second shaft. KT2 will be GJ by L2. So, now you can able to see that because these 2 natural frequencies are same, we can able to equate them. So, if we equate them, we will get KT1 by IP1 is equal to KT2 by IP2. Now, you can able to see if we substitute KT1 and KT2 in this expression, we will get, because most of the things are common, L2 by L1 is equal to KT2 by IP1. I am repeating this. So, when we substitute IP1, KT1 and KT2 from these expressions, we will be getting GJ L1 IP1 is equal to GJ L2 IP2. So, this will give us, because we have some terms common, they will get cancelled. So, we will be having L2 by L1 as IP1 by IP2. So, you can able to see that the node position will be inversely proportional to the mass moment of inertia. This is one of the expression, and we know second expression that total length is L1 plus L2. So, we have 2 equations for obtaining the L1 and L2, we can able to solve these two equations to get the L1 and L2. If we solve it, we can able to get the node position. So if we solve this, we will get this as and once we know the L1, that is the node position, L2 can be obtained. L2 will be L minus L1. So with this procedure, we can able to get the node position, which is very important because here even the angular displacement is not taking place, but stresses will be maximum because either side of the node we have angular displacement opposite to each other. So maximum stresses will be more here. So we considered two disk system. In this particular case, we consider the shaft which was connecting these two disks were uniform. Now we will consider a case in which the shaft which is connecting these two disks are having different cross section in between, and for that case how to analyze such system. So in this particular case, we have one disk and second disk, and that is connected by shaft having different dimensions in between, like this. So this is IP1, this is IP2, length of various stubbed shaft or L1, L2, L3, even their diameter are different, D1, D2 or D3. So if we neglect the mass moment of inertia of the shaft, only if we consider the disk. So this particular system is in some way is identical to the previous rotor system, in which we had two disks but connected by a uniform shaft. So if by some means we can able to convert this particular system to this one, then whatever the analysis we presented earlier will be valid. So in this particular case, this two system will be equivalent when we have the torsional stiffness of this system and this system same. So if they are same and polar moment of inertia are same, these two system can be identical. So if this is the stiffness of the equivalent system, and let us say this is one of the diameter of the original shaft, D3. So the length of the shaft of this will be, we need to find out what should be the equivalent length, so that the stiffness of this and this are same. And if we can find out, then the previous analysis will be valid here. So basically we can able to equate the stiffness, torsional stiffness of this two system. So you can able to see that the stiffness of this, because these are connected in series, so equivalent torsional stiffness of this system will be given as so these are the stiffness of first shaft segment, second shaft segment and third shaft segment. That means because we already know in general KT is given by Gj by L. So this KT can take value of 1, 2 or 3, depending upon that this J1 and L1 and expressions will come, because J depends upon the diameter. So if we substitute this, you can able to see that we'll be getting L equivalent in this divided by J equivalent L1 by J1 plus L2 by J2 plus L3 by J3, and basically J3 and JE are same because we are converting the equivalent system to the diameter of the third shaft segment, and if we multiply with JE, we will get this as JE plus L2, sorry, this is E and this is 1, this is JE by J2 and L3 because J3 and L3 are same. So you can able to see that this can be written as equivalent length of first shaft segment, equivalent length of second shaft segment, and equivalent length of the third shaft segment. So this is the total length of the shaft segment. So with this we can able to obtain the equivalent shaft segment length, and now we can able to apply the previous analysis to get the natural frequency of the system, in which we had the 0 natural frequency and 1 flexible mode natural frequency. So all the analysis will be similar to the previous one. So in this case, again, to analyze that, we need to assume that this is mounted on frictionless support, which is as such not providing any friction. So in this particular case, we have converted the step shaft to equivalent shaft system of uniform diameter. So let us see what is the difference, especially if we obtain the node position with the previous analysis. In this particular case, when we want the node position in the stepped shaft, so if this is the node position in the equivalent shaft corresponding to the second shaft segment, you will see that you can able to see that this dotted line is representing that from here to here is the equivalent of the second shaft segment, and if node is here, that means the position from this end is AE and from this end is B of that node. So the ratio of this A by B will be same in the original shaft segment, this A and B. So node will be somewhere here, which will be in the same proportion as in the equivalent system. I will summarize. So today we saw a very fundamental aspect of the torsional oscillation, how it takes place in a rotor system, which is itself is rotating and at some nominal speed, but above that there is some variation of the angular displacement, and because of that some small changes in the angular velocity would be taking place. And this particular analysis we have done for single mass rotor system and 2 mass rotor system, and we have seen that for 2 mass system, one of the natural frequency of 0 and another was non-zero, that was flexible mode, and we had the concept of the node position in that 2 disc rotor system where the displacement was 0, but we will see that at that position where the node is there, the stresses will be maximum, because either side of that particular node there will be a relative twist will take place. In the next class we will extend this particular analysis for 3 rotor system, and then we will find that whatever the procedure we are following, especially using the Newton's second law, we are obtaining the governing equations, will be more cumbersome, especially when we have more degree of freedom of the system, and then we will take up some more systematic method like transfer matrix method and finite element method. Now we will see this Campbell diagram in more clear picture. So you can able to see that we have drawn the same plot, and in this there are 4 lines, the solid lines you can able to see. So first one is this one, second is this one, third is this dotted line, third is another dotted line. And at one particular speed, if we let us say want to see intersections are these are the natural frequencies, these are corresponding to the forward world, these are corresponding to the backward world. Regarding the critical speed, this line is the omega equal to nu line, and intersection of this will give the first critical speed is here. This line is not intersecting the second line, so there is no critical speed corresponding to this. Similarly, if we draw another line, omega is equal to minus nu, this intersect at here, this is first backward critical speed and this is the second backward critical speed. So you can able to see that we got 3 critical speed, 1 forward and 2 backward, but another forward was absent.